Factory defects, the weak electric motor that powered NASA's energy, the hook and the universal defect. In 1959, inside the laboratories of NASA's Glenn Research Center, physicist Harold Kaufman completed the first test of his revolutionary space propulsion system. When he activated the motor for the first time, the measurement was devastating, a laughable force of mere micronewtons, equivalent to the pressure exerted when typing a computer key. While chemical engines of that era generated millions of newtons of thrust, Kaufman's motor could barely push its own structure. His colleagues laughed openly. Apollo program engineers dismissed him entirely. But there was something nobody realized. That pathetic defect, that humiliating weakness, was precisely what would make reaching the outer edges of the solar system possible. How could such a feeble motor become NASA's most powerful technology for space exploration? The answer lies in a fundamental miscalculation about what force actually means in the vacuum of space. The technical impasse. The problem was mathematical and brutal. Chemical rockets burn fuel to expel mass at high velocity, generating instantaneous thrust through Newton's third law. To escape Earth's gravity, you need tremendous and immediate force. But there's a hidden curse in this equation. The more fuel you carry, the more mass you must accelerate, creating a vicious cycle. A rocket to Mars would need to carry so much propellant that 90% of its weight would be nothing but fuel. For missions beyond Jupiter, the mathematics simply didn't work. The necessary fuel would exceed the mass of entire buildings. Since 1906, when Robert Goddard first wrote down the idea of electric propulsion, physicists knew that accelerating ions with electricity could theoretically be more efficient. But physics was cruel. Any electric motor strong enough to compete with chemical propulsion would be absurdly heavy and consume nuclear energy equivalent to a small city. The defect wasn't merely technical, it was existential. Either you had force without efficiency or efficiency without force. There was no middle ground. The intentional error. Harold Kaufman made a heretical decision in 1959. He embraced the weakness. Instead of trying to make the ion thruster compete with chemical engines in brute force, he did the opposite. He intentionally designed a ridiculously weak motor, but one that consumed electrical energy instead of fuel mass. The secret lay in a radical conceptual inversion. Kaufman bombarded mercury atoms with electrons, stripping electrons from the atoms and creating positively charged ions. These ions were then accelerated through electrostatic grids to velocities of 30 to 50 kilometers per second, 10 times faster than chemical exhaust gases. The instantaneous force was pathetic, but the exhaust velocity was tremendous, and in the vacuum of space, where there's no friction, even an ant pushing produces continuous acceleration. Kaufman understood something that chemical rocket engineers ignored. In deep space, accelerating for years with minimal force beats accelerating for minutes with maximum force. The first functional ion thruster was ready for testing. It was weak, it was slow, it was impossible to use on Earth. But in vacuum, where pure Newtonian physics reigns absolute, that weakness would become an unbeatable advantage. The doubt and the resistance. When Kaufman presented his ion thruster to the space program in 1960, the reaction was institutional contempt. Apollo project engineers laughed openly. You need 3 years of continuous operation just to match 1 minute of acceleration from a chemical motor. The American Congress, funding the space race against the Soviet Union, demanded spectacular and immediate results. Thrusters that took years to accelerate seemed like a joke. Worse still, liquid mercury was the chosen propellant, a toxic metal that evaporated and contaminated equipment. Initial tests in 1963 failed repeatedly, with valves jamming and electrostatic grids corroding. The suborbital mission SER-T1, planned for July 1964, would be Kaufman's last chance to prove that weak motors had a future. But there was silent sabotage happening. Nobody at NASA truly believed this would work. The budget for electric propulsion was crumbs compared to Apollo's billions. Kaufman was trying to sell long-term efficiency to an agency addicted to short-term explosive spectacles. The weak motor was being suffocated before it could even fly. The payoff, the great revelation. July 20th, 1964, California skies. The Scout suborbital rocket launched, carrying 2 experimental thrusters, Kaufman's ion thruster and a competing model from Marshall Space Flight Center. For 31 minutes in the vacuum of space, while the SERT-1 capsule followed its ballistic parabola, Kaufman's ion thruster functioned perfectly. The blue beam of mercury ions, accelerated to 30 kilometers per second, was detected by sensors. Perfect telemetry. Continuous and stable thrust. Marshall's competing thruster failed completely at ignition. Kaufman had proven the impossible. Weak motors work in space. But the real shock came 6 years later. In February 1970, the SERT-2 mission placed 2 ion thrusters in Earth orbit powered by solar panels. The planned mission was 6 months. The motors operated for 8 consecutive years, being restarted hundreds of times. No chemical engine had ever operated for more than a few minutes without destroying itself. The weakness had become the perfect characteristic. Low thrust meant low wear, allowing virtually eternal operation. The factory defect was actually infinite durability. The consequence of success. SER-2's success created a new problem: premature enthusiasm. In the 1980s, NASA and aerospace manufacturers began adapting ion thrusters for commercial satellites. But mercury, Kaufman's original propellant, was an environmental time bomb. Mercury vapor condensed on solar panels, reducing energy efficiency. It contaminated electronic components. And there was the political problem. Launching kilograms of toxic mercury into space on rockets that occasionally exploded in the atmosphere was an environmental disaster waiting to happen. Regulatory agencies began pressuring for mercury bans in space applications. The industry tried alternatives. Cesium, also toxic. Sodium, also problematic. Each substitution brought new technical defects. Worse still, first-generation ion thrusters consumed tremendous electrical power, requiring gigantic and heavy solar panels that negated part of the mass advantage. By 1985, NASA's ion propulsion program was again on the brink of cancellation. The weak motor had proven it worked, but now had a secondary factory defect: dependence on toxic materials and excessive energy. The technology needed a second reinvention. Public crisis and the scandal. The breaking point arrived in 1994. The Russian Mars 96 mission, equipped with experimental ion thrusters, failed spectacularly at launch. The probe crashed into the Pacific Ocean, carrying radioactive cesium and mercury. Although the thrusters weren't the cause of the rocket failure, international media exploded with alarmist headlines about toxic space engines. Environmental groups pressured for an international moratorium on ion propulsion. The technology's reputation was destroyed. Western space agencies faced a choice: abandon decades of research or find non-toxic propellants that worked. The problem was that all heavy metals, mercury, cesium, had been chosen precisely for their superior ionization properties. Replacing them meant accepting inferior performance. But there was one substance nobody had seriously considered: xenon, an inert, noble gas and completely non-toxic. The problem? Xenon was extremely expensive, weighed more than mercury when pressurized, and its ionization required even more energy. Proposing xenon as propellant in 1995 seemed like economic insanity, but Hughes Aircraft and NASA Glenn decided to take the risk. If it failed, it would be the definitive end of ion thrusters. If it worked, it would be complete redemption. The elegant remedy. The solution came from radical reverse engineering. In 1998, NASA's Deep Space One probe became the first deep space mission powered exclusively by ion propulsion, using xenon as propellant. Engineers compensated for xenon's ionization difficulty by increasing electron bombardment and redesigning electrostatic grids with geometry optimized by supercomputers. Energy consumption dropped from 10 kilowatts to just 2.3 kilowatts, thanks to new generation gallium arsenide solar panels. And xenon, despite its cost per kilogram, proved incredibly economical. Deep Space One operated for 678 days using only 73 kilograms of xenon. An equivalent chemical rocket would need tons of propellant. The mission was an absolute success, proving that non-toxic and efficient ion propulsion was viable. In 2007, the Dawn probe used ion thrusters to become the first spacecraft to orbit two different celestial bodies, Vesta and Ceres, a feat impossible with chemical propulsion. Kaufman's original weakness had transformed into the definitive characteristic, low but continuous thrust, allowing multiple orbit changes without carrying extra fuel. The DEFECT of 1959 was now NASA's standard of excellence for long-range exploration missions. The philosophical legacy. The ion thruster's history exposes a brutal philosophical truth about innovation. Defects only exist in specific contexts. Kaufman's motor's tremendous weakness was a lethal defect on Earth, where gravity demands brute force. But in the vacuum of deep space, where there's no friction and time is abundant, that same weakness became supreme efficiency. In 2025, over 500 spacecraft equipped with electric propulsion orbit Earth or explore the solar system. The Psyche mission, launched in 2023, uses ion thrusters to reach a metallic asteroid 370 million kilometers away. The technology that seemed like a joke in 1959 is now indispensable. The lesson transcends engineering. What appears as categorical failure in one environment can be decisive advantage in another. Goddard imagined electric propulsion in 1906, but it took 58 years for Kaufman to build the first functional prototype, and another 34 years for Deep Space One to prove commercial viability. Radical innovation demands generational patience. The weak motor teaches that intentionally accepting limitations rather than denying them can open paths that brute force could never reach. In deep space, slow and steady doesn't just win the race, it becomes the only way to finish the course. Factory defects has just revealed how history's weakest motor became NASA's most powerful technology. Harold Kaufman embraced weakness when everyone demanded strength. He transformed pathetic micronewtons into interplanetary exploration. He proved that in the vacuum of cosmos, persistence surpasses power. The intentional error of 1959 now propels hundreds of missions. The error that made history. What defect are you avoiding that could be your greatest advantage? Don't forget to subscribe to the channel, activate notification bells, and leave in the comments which defective invention you'd like us to investigate. Share this video with someone who needs to understand that weaknesses can be disguised strengths. Until the next genius failure.